Right, so this is lecture 8, that's the week 9 and that's the last class of week 9. So we have only 1 week remaining. That week will be wrap up about how you can apply all these things that you learn in a sustainable way. Most of the time when you think of environmental engineering, we think of cleaning up pollutions, but actually it's a little more than that. It's You have to also manage your environment in a way that you can actually create resource. So now we are not just mitigating pollutions, but also we are creating resource out of the pollutants. For instance, if you think of wastewater treatment plants, this is no longer called wastewater treatment plant. It's called resource recovery plant, because what we are doing here is actually recovering water, which is the main resource. We are also recovering nutrients, other stuff that is normally we waste. So same thing when you think of biosolid or any kind of solid waste, we also try to find a way to extract some resource from it. So all those things, how the new technology works, all that we are going to discuss in the next week of class. But today, this is the last class in terms of the things that is relevant for your quantitative experience, in the sense that you'll know how to calculate stuffs in this class. Next week class is not more quantitative; it's more qualitative, and also we'll discuss about finals. Okay, so air quality modeling. This is very important because if you know that we are in the middle of pandemics, a lot of times we thought if we just wash our hand and do all that stuff, it minimize the chance of infections. But if you realize, the anytime you are talking about viruses, it's more on air transmission. So surface to surface interactions, it has some risk, but it's not as much as inhalation risks. So what we are going to learn today is how you can apply what you learn in this class to understand the rules and regulations in place for coronavirus. So this is pretty applicable in that sense. Um, okay, so a couple of announcements. Homework 6 is due today, but I really want you to try to understand it's not rushing. So I increase the window, window to next on Thursday, which is tomorrow midnight, so that you can at least try and instead of rushing, because I want you to understand the questions. This is important for the final. Homework 7 will be released today. This is based on the last week of class, as well as last week in the sense anything waste management we taught in the last few weeks, and also air quality. So this is the last homework, which will be due on Wednesday next week, and I'll immediately release the solutions because some of the questions are relevant for finals. We'll talk more about final next week, type of questions and all that. So one thing I learned from midterms is that the the questions and other things are sometimes it took longer for some of you. So I have seen some of you didn't finish it. So I didn't want to use that as a options in final. So I'll extend the time to probably 6 hours instead of 4 hours that I put. That way you have at least enough time to work on it. So we'll talk more about next week on that. Office hour, no office hour because we had it yesterday. But I am available by emails. If you want to meet, you can always send me emails and we can set a time. Um, that is always option for you if you are concerned about anything. At this point, I would encourage you to look at your homework grades, because some of the grades that I supposed to update, I didn't update it. So it's time for you to check whatever TA graded. You got to check, if there are some places where you can get some points, because every TA has general. I give a guidelines, but it's up to them to decide. I don't control it, but roughly, it's your responsibility to check if any places TA accidentally or for any reason takes points up that you think you'll get something bad. So review your homeworks, and again, these are all you can do it until the end of final weeks. So I'm not going to update the grades until I get confirmation from all of you that you are all revise your grades. Um, Again, keep asking question on campusware, and the materials that is covered in this class or in last week, this week of class is chapter 7 of the textbook, that's air pollutions, and the sections that relevant for today's class particularly is 11 and 12 in that chapters. Let me see if there is any. Um, yes, I record the office hour. It's all on YouTube, so always check on YouTube because anything I record within 1 hour of I upload it. Okay, so learning objective. Today is more quantitative aspect of air pollutions. Last class, I just brushed off everything about what are the air pollutants we should be concerned about. I expect you to read those. I'm not going to read it for you here, so I didn't really write any kind of materials here. But it's your responsibility to understand what those different pollutants are, where they're coming from. It's important for your learning. Okay. Um, so the most important thing that we are going to learn today is how particulates transport in air. Okay. Um, yes, there is a one announcement. Thanks for reminding. Quiz 3 is next class. Next class means next Monday. Uh, um, the only updates that I want to say is I decided that this quiz, what I'll do is because we have two quiz, so best of two quizzes. Okay, so that means whichever your best performance in quiz 1 and 2 and 3, I will consider best of two of the quiz. So this quiz is relevant in the sense that if you have done well in the any of the previous quiz, this is an important quiz for you. If you have done, let's say, 100% in the previous two quizzes, if you even you didn't attend this one, you will not results will not be affected. So again, just want to say this is best of two quizzes will be considered in your grades. I wanted to do that because I know that lots of you have to prepare for finals. I don't want to add another stress for your work life. So prepare well for the quiz 3. I'll send more information by email. What is that? Basically, it's everything after midterms except this week of class. This week of class. Okay. So what essentially it will cover is um, wastewater, wastewater treatments, and waste management. Okay, so if I want to write, now let me double check what those lectures are, that we don't have to be confused about it. So we, let's see, lecture 12. So lecture 15 is waste management, lecture 16. Okay, so lecture 15, 16. Let's see, lecture 13. So lecture 13 was all about midterms review, so it was not really any class. Let's see, lecture 14 are wastewater treatment. So again, it's after lecture 13 or something. So after 13, just check the materials again, materials related to wastewater treatment plants and waste management. Okay. All right, so any questions? So anything about grades, so let's not discuss today. Let's discuss next week for the finals.
Is
I
air
would.
pollution going to be on the quiz?
Which one?
Anything from today?
No, anything not from this week, not in the quiz. So anything about air quality is not part of the quiz. Okay. Mm, okay, so I know that also I want to say that some of you are concerned about the grades because you have option to choose pass or no pass. Obviously, nobody's failing this class, but if you wanted to do that, it's okay. I'm not really. It's not my place to decide what you should do. But you got to know your midterm score, so I'm aware of that. So I'm asking TA to grade it by Thursday midnight. But if you want to know it earlier, then you send me emails and I'll personally grade that exams tomorrow and send it to you. And that way you know your actual grade for the midterms. And we at this point I don't know what's the distributions are look like. So far, I just see that it's what we expected. 50 people, at least one question we finish grading completely, at least one TA, because each TA grade one question each. That way it's consistent across the all students, and based on that distribution, so it seems like 50% get more than 90% in that particular question. So I so far I have not seen anything that warning. But as I said, we right now don't worry anything about it because midterms is still some percentage only, not everything else. You have quizzes, you have homeworks. Homeworks, I expect you to get the full percentage. That's why I ask you to check anywhere we can get points from there. And next thing is the final. Final is still a big part of the. And final, if you understand, this is not cumulative, so you have only few chapters to read. So that's why it's a lot easier to do well in the finals. But at the same time, final is also kind of more like a mass balance perspective. So I'll give you lots of examples next week for you to work on. So I hope that you will do very well in finals, and also I extend the time so that time is not a factor for your final. So overall, all that, if you do well in final, you still can get a very good grades. So let's not discuss about grades so far. Let's work on the what we have in control. Once we have the final midterms grade, then we can discuss if specific thing apply for you if you want to know more. There is a The question was going to have any more homework assignment. As I said, this is homework 7 will be released today. So that's about air quality and waste management. Not after that. Obviously, next week is final. So not final week. Okay. Any other questions related to homeworks or again everything announcement is here if you want to know. Homeworks when will be released. It's all air quality as well as waste management. Um, so literally you have homework 6 and 7 for final. Okay, and that's why I say homework 6 is very important because it has more questions related to wastewater treatments. So that's why I want you guys to try the homework 6 as much as possible and learn every questions, which is due on Thursday night now. If you don't submit by that time. Um, Again, quiz is next class Monday, and it's on wastewater as well as waste management. Nothing on air quality. So not air quality. Okay, which is this week of class. Don't expect you to read that for the quiz. Again, best of two quizzes will go to the finals, the final grade. So you it's your best interest to do well in the third quiz. But if you don't attend, no, I'll take the first two quiz of your whatever performance you had. Um, Again, the same concept. It's a 20 minutes, the same times, like the same windows, 24 window, 24 hours window. But once you open the quiz, you have 20 minutes to answer. This will help you prepare for the final small short question. So it's very important that you take it. Okay. All right. So 20 minutes into the class, let's discuss about today's lectures. Air quality is very exciting class. The reason is it's a lot of relevance for coronavirus. You know how it transmits. So you got to understand that concept. So what you're going to learn today is how particulates, small fine particulates, move in air, how far it can migrate from the source, and how also what it does in your lungs. So that's important for you to understand that. As you see in this picture over here, there are different size of particulates from all the way from 100 nanometers or zero point 0.1 micrometers, micron size to 30 micron. So it just shows that these are the size relevant for air transport, but they are stuck in a different place in your in your nodes. For instance, anything 10 microns or more than 5 microns, they cannot migrate too far because they're so big that it will be removed by the hair in your nodes. And anything smaller, they can start going down deeper and deeper. Once it get to the bacterial level, 1 to 2 micron, they can actually get into lungs. Um, so that's why our lungs has defense mechanism for bacteria. But if it is really small particle, less than 1 micron, then it can goes into the airways. If it is virus, which is the size is 0.1, roughly this is the virus size. Coronavirus size is roughly 100 nanometers. They can actually penetrate and get into the different parts. That's why viruses are very dangerous. So you'll learn about that. And then you'll also learn about what affects the concentration of these different pollutants in air. You'll also learn how to understand how these pollutants move inside your home. For instance, if somebody is smoking in your home, how far it can migrate. Another things to understand is how you can change the ventilation system such a way that any viruses emitted can be removed from the systems faster. Then also you learn about outdoor pollutions. For instance, if you have a emission stack, you are near industry which has a big chimney, in how far those pollutants will migrate. So this particular one, I will not have most example today in the class, but I'll provide more example after the class, like I did for the homework. So you should learn how those from those particular examples. Again, the real world implications at the end of this class, we'll discuss this, how safe it is to go to the restaurants and sit like you see over here. There's a block, physical block, what it does. Does it really effective? What does it affect? It is to some, it's better than nothing, but what it does, you got to understand that so that you know the risk that you are taking for being there. And the second one is the 6 feet distance. So we know that this rule is in place that you have to be far away 6 feet from another. Then you can remove your mask and still you can minimize your risk. Okay, there is never risk is zero. Always risk is more than zero. But still, they decide that this is a compromise one can take. So you should understand why that 6 feet. So we'll calculate in this class so that you know what that 6 feet means. Uh, okay. So first of all, because a lot of things we are going to discuss today is related to coronavirus. So I want you to watch this video because this is a interesting video about what it does. Same thing you can understand if you of other particulates. So what I'm going to do is I'm going to stop share this one. I'm going to share the YouTube. Okay. So Google Chrome. Let's see if I see I want the computer music to go through. The sound should be from the computer. So let's see. I know there is options where we could do that, but I could not. Let's see. Well, I just put the microphone near it so that you hear.
This is SARS-CoV-2. It belongs to the family of coronaviruses named for the crown-like spikes on their surfaces. SARS-CoV-2 can cause COVID-19, a contagious viral infection that attacks primarily your throat and lungs. What actually happens in your body when you contract the coronavirus? What exactly causes your body to develop pneumonia? And how would a vaccine work? The coronavirus must infect living cells in order to reproduce. Let's have a closer look. Inside the virus, genetic material contains the information to make more copies of itself. A protein shell provides a hard protective enclosure for the genetic material as the virus travels between the people it infects. An outer envelope allows the virus to infect cells by merging with the cell's outer membrane. Projecting from the envelope are spikes of protein molecules. Both a typical influenza virus and the new coronavirus use their spikes like a key to get inside a cell in your body, where it takes over the cell's internal machinery, repurposing it to build the components of new viruses. When an infected person talks, coughs, or sneezes, droplets carrying the virus may land in your mouth or nose and then move into your lungs. Once inside your body, the virus comes in contact with cells in your throat, nose, or lungs. One spike on the virus inserts into a receptor molecule on your healthy cell membrane like a key in a lock. This action allows the virus to get inside your cell. A typical flu virus would travel inside a sac made from your cell membrane to your cell's nucleus that houses all its genetic material. The coronavirus, on the other hand, doesn't need to enter the host cell nucleus. It can directly access parts of the host cell called ribosomes. Ribosomes use genetic information from the virus to make viral proteins, such as the spikes on the virus's surface. A packaging structure in your cell then carries the spikes in vesicles, which merge with your cell's outer layer, the cell membrane. All the parts needed to create a new virus gathered just beneath your cell's membrane. Then, a new virus begins to bud off from the cell's membrane. Now, with the virus spreading in your body, how can you develop pneumonia symptoms? For this, we'll have to look into your lungs. Each lung has separate sections called lobes. Normally, as you breathe, air moves freely through your trachea or windpipe, then through large tubes called bronchi, through smaller tubes called bronchioles, and finally into tiny sacs called alveoli. Your airways and alveoli are flexible and springy. When you breathe in, each air sac inflates like a small balloon. And when you exhale, the sacs deflate. Small blood vessels called capillaries surround your alveoli. Oxygen from the air you breathe passes into your capillaries, and then carbon dioxide from your body passes out of your capillaries into your alveoli so that your lungs can get rid of it when you exhale. Your airways catch most germs in the mucus that lines your trachea, bronchi, and bronchioles. In a healthy body, hair-like cilia lining the tubes constantly push the mucus and germs out of your airways, where you might expel them by coughing. Normally, cells of your immune system attack viruses and germs that make it past your mucus and cilia and enter your alveoli. However, if your immune system is weakened, like in the case of a coronavirus infection, the virus can overwhelm your immune cells, and your bronchioles and alveoli become inflamed as your immune system attacks the multiplying viruses. The inflammation can cause your alveoli to fill with fluid, making it difficult for your body to get the oxygen it needs. You could develop lobar pneumonia, where one lobe of your lungs is affected, or you could have bronchopneumonia that affects many areas of both lungs. Pneumonia may cause difficulty breathing, chest pain, coughing, fever and chills, confusion, headache, muscle pain, and fatigue. It can also lead to more serious complications. Respiratory failure occurs when your breathing becomes so difficult that you need a machine called a ventilator to help you breathe. These are the machines that save lives and that medical device companies currently ramp up production for. Whether you would develop these symptoms depends on a lot of factors, such as your age and whether you already have an existing condition. While this all sounds scary, the push to develop a coronavirus vaccine is moving at high speed. Studies of other coronaviruses led most researchers to assume that people who have recovered from a SARS-CoV-2 infection could be protected from reinfection for a period of time. But that assumption needs to be backed by empirical evidence, and some studies suggest otherwise. There are several different approaches for a potential vaccine against the coronavirus. The basic idea is that you would get a shot that contains faint versions of the virus. The vaccine would expose your body to a version of the virus that is too weak to cause infection, but just strong enough to stimulate an immune response. Within a few weeks, cells in your immune system would make markers called antibodies. which would be specific for only the coronavirus, or specifically its spike protein. Antibodies then attach to the virus and prevent it from attaching to your cells. Your immune system then responds to signals from the antibodies by consuming and destroying the clumps of viruses. If you then catch the real virus at a later stage, your body would recognize it and destroy it. In other words, your immune system is now primed. Collecting evidence on whether this will be possible, safe, and effective is part of what's taking researchers so long to develop a vaccine. It's a race against time to develop a vaccine amid a pandemic. Each step in vaccine development usually takes months, not years. An Ebola vaccine broke records by being ready in 5 years. The hope here is to develop one for the new coronavirus in a record-breaking 12 to 18 months. While all of this will take time, stay home if you can to protect the most vulnerable. And don't forget to wash your hands for at least 20 seconds and as often as possible. This video was a collaboration between Nucleus Medical Media and the What If channel, where we usually dive into hypothetical scenarios about the human body.
All right, so it's a video worth watching. Thought now we'll let me stop share the video so we can watch the screen. Right. So what we learn here is that coronavirus can get into the extreme part of your blood, right at the edge where the exchange of blood, exchange of oxygen happens. So that's why the oxygen level decreases if one has a coronavirus. But no, the coronavirus is not the only pollutants. As you, if you read all the other materials that we share on the textbook, it can also have a lot of other pollutants. That's dissolved pollutants, sulfur dioxides, nitrogen dioxides, carbon monoxides, all the other particulates. Each of them has different diseases. So as you can see, these diseases could vary from different types of respiratory disease, including cancers, lung cancer. And lung cancer is something that's very hard to detect. But by the time it's detected, it's a kind of stage 4. And so that's why the survival of lung cancer is very low, partly because it's detected very late. And not just only that kind of disease, there are also diseases that affects other organs. For instance, if you see carbon tetrachlorides, which is emitted from the old refrigerators or other kind of solvent, they can affect liver. There are other diseases that could be, for instance, carbon monoxides can also affect your heart rate. So these are different things that are affected, but these are all sourced from air. So it's very important that we understand how to model these pollutants so that we know how much we are exposed to. So that's part of the things we are going to learn. But the biggest thing about one of the things that is very difficult to do air pollution mitigation is because this is open area. Unlike water, you can stop the flow of water, you can channel them. But air, once it's released, it's there. The entire atmosphere is open for everybody. So it's very difficult to contain it. So that's why it's very hard. And second, there are all these different pollutants. So it's how to know what air quality can be. So it is very difficult to decide air quality based on one specific pollutants. That's why air quality index is developed, which account for 5 different pollutants. One is ground level ozones. It's different from the atmospheric ozone, which is above the atmosphere. Then particulates, including viruses, carbon monoxide, which is carbon monoxide, sulfur dioxide, nitrogen dioxide. These are produced from incomplete combustions of fuel. So if you think of car exhaust, all these carbon monoxide, sulfur dioxide, nitrogen dioxide comes. Again, the reasons sulfur dioxide usually come from coal because coal has lots of sulfur. Nitrogen dioxide is because of any combustions in engine oil, uh, because atmosphere has 70% or 78% nitrogen. So when you pump this air through it for oxygen, it also combusts the nitrogen. That's why nitrogen dioxide or other forms form. And carbon monoxide because carbon burning. So you see this different range we discuss. Up to 500 is monitored. Doesn't mean that you cannot exceed 500. It just means that above 300 is very hazardous. And the way it is developed is based on what it can cause. So most of the time, air quality index 0 to 50, you can actually check any locations. If you search air quality index monitoring, you can look for air quality index for your zip code for entire worldwide. Now this is being developed, so you can search that. So for instance, you can check what is the air quality index in Westwood today or UCLA campus. You should be able to find all that. So what it means that it's a guidance to show what kind of action you should take, who should be at risk. So 0 to 50 means no health impact, no measurable health impact. Moderate means it's important for sensitive people who are don't want to expose to yourself in a moderate air quality. For instance, if the air quality is moderate, you should not jog outside. You should not run outside for too long because you are breathing so faster that you will inhale many of them. In general, LA air quality is bad, around 51 to 100. Depends on the time and locations. Particularly if you are living near the freeway, that's the exposure is much higher. So that's why a lot of times you see the housing market right near the freeway, the cost is a little bit less because of noise pollution as well as the air quality. And then obviously 101 to 150, 151 to 200 becomes unhealthy. Every time there is a wildfire nearby, the quality goes to unhealthy to very unhealthy levels. If you're right near the where the fire is happening, that's where it becomes hazardous. It's extremely unlikely to have hazardous air pollutions far away from there because most of the particulates settle down. But country like city like Delhi in India that has always hazardous level in winter because the quality is pretty bad. So again, as you know, air quality index is not just one pollutant; it's five different pollutants. I listed it here, and so it's a combination of all that. So for each pollutant, the range are given here, and based on the time they measures. Based on the sensor, it measure every 1 hour or every 24 hours. Many of these are measured by a satellite now, so it has more continuous measurement. Again, volatile organic carbon, this is one specific type of pollutants which are important, but it's not included in the air quality index because very difficult to measure. It's so many different types of pollutant, but it indicates, yeah, its presence indicates how much ozone, ground level ozones that you might expose to. The reason is volatile organic compounds can interact with sunlight and nitrogen oxide, which is produced from combustion, to form smog. It will also form ozones, and ozones are extremely reactive, so that's why it's not as good to have those ground level ozone. Because of that, we have lots of clean regulations. So the first one is 1970 Clean Air Act. That's mostly it controls the five main pollutants: carbon monoxides, nitrogen dioxide, sulfur dioxides, and particulates. But in 1990s, because a lot of leads during that time, gasoline has lots of lead because of the lead pollution spread across. So that's why it was included. Ozones and leads are included in the 1990 Amendments Act. So these are just, you should read those. It's only one page. So read what it cover, what it doesn't cover, and all the challenges. But most importantly, in this class, you are going to learn about modeling, how far the pollutions travel. For instance, here you saw that big city release a lot of pollutants, industry release a lot of pollutants. It spread across the entire continents. In fact, what's pollution happen in China goes to US, and vice versa. US goes to Europe. So it's not, it's not about just the pollution what is happening here. It can affect the people's miles and miles away. even though they don't create those pollutions. So the very first thing modeling is how long a droplets or particulates stay in the air. If you want to measure this one, so let's see if we can do that calculations. Again, this is something you learned that before. We just apply again. This is you learn how long a particulate can suspend in water by settling velocity. Exactly the same equation here. So settling velocity, what you learned before is velocity. That's how fast it can settle. Um, uh, so settling velocity um, is a function of the density difference of particles with medium they are suspended in. Here, this is air. In reality, air can be zero because the density of particulate is way higher than the density of air, because it's a molecule level. So roughly, you can ignore that one um, for these calculations. And then you have what is remaining is this size. Okay, so that's acceleration due to gravity. This is particle density. Particle density. This is gravity constant. So acceleration due to gravity, that's 9.8 meter per second square. Then this is the size or diameters of the particulates, and this is viscosity of air. And that number is given here. Okay, 0.172 gram per meter and second. Okay. So now that you have known the velocity, if you want to calculate how long a particulate will suspend, let's say you know the height. Okay, this is the height, this is the meter. So that means the time would be height divided by velocity, because it migrates. If a particle is here, it will just move that to settle here. You have to know that this is the velocity. Then height divided by velocity, you get the time. Okay, so as long as you know so all you have to do is calculate this value. So h by velocity will be h. If you substitute velocity, it will be 18. Then viscosity divided by g particles d square. So if you want to do that, so at the end of the class, we'll discuss, you will apply all that for coronavirus. For let's say apply for regular particulates. Find the settling velocity of a spherical droplets of water with a diameter 2 micrometers and estimate the residence time of such particles if they are uniformly distributed in the lower 1,000 meters of atmosphere. And then determine the removal rates. Okay. So first, let's calculate the velocity. So velocity again is, if you see these equations, g density of particulates diameter square divided by 18 mu.
Why did you say that the density was practically zero for the air density?
Why I said zero?
Yeah.
It's not zero. The difference is the particle
Very
density.
minimal.
Let's say 1.1 gram per. I'm just throwing a number.
Okay.
That is so way like 10,000 times less, that difference is almost not same as the particles. So that's why it really, in all practical purpose, you don't have to write the air density.
All right. Thank you.
Okay. So 9.8 meter per second square. Density, let's see, what's the density of this? It didn't say here, but it has, let me see. For example, so usually any dust particulates density is around 2.6 gram per centimeter cube. I just want to make sure that this is this is the example in the book. So I just want to see what they assume. If nothing is given, you can write 2.5 or 2.6. Let me see if there is a table that provide the density.
Professor, would the problem says it's a droplet of water, so would we just take it to be
Oh, you're right. So this is a droplet of water, so it's density of water, that's you can write. So I'm sorry. Good. So water density is 1 gram per centimeter cube. That's water, right? Okay, so let's write that one. 1 gram per water. So that's something, if you say in meter cube, usually air is the volume is meter cube. So is a the one meter cube is, so I'm gonna write this one more accurately. So 1 meter cube is 10 to the 6 centimeter cube. It's 1 meter 100 centimeters, so that's why it's 10 to the 6 meter cube. So this become 10 to the 6 gram per meter cube for water. Okay, so if you write this one, density is 10 to the 6 gram per meter cube times diameters. Diameter is 2 micron, so it's a 2 times 10 to the 6 meter square. Okay, divided by 18 times viscosity. Viscosity is, as I said, 0.0172 gram per meter second. Okay, so second cancel, 1 meter cancel, then 2, this is meter square cancel here, so that will be gram cancel, so it's meter per second. So this value, as the book says, 1 point, I didn't calculate whatever the book says, I'm just gonna write it here. Okay, so that first, that's how fast it migrates, faster, which is about, if you write that in hour, it will be roughly it will be 0.5 meters per second per hour. Okay, so half meter per hour roughly it migrates for the droplet. So if you think of coronavirus, the virus's droplet, or if you think of the droplets that we emit when we cough, it's roughly around 1 to 5 microns max. Mostly it's 5 micron. If you can see the droplet, it's around 5 micron. For instance, in pictures, the droplet size is roughly 5 micron. So based on that, you can see what that velocity would be. It will be even much more or much less than that. Let's see what's the, why is the diameter is to the -6. You're right, to the -6 micron. So its micrometer is 10 to the -6. Right, so it's fine. So this is all correct. Okay, so let's calculate how long it goes, how far it is stays in the air for 1,000 meters. So again, the time will be distance, height would be height by velocity. So that would be, height is 1,000 meter. That's what is given here. Divided by velocity is 1.27 to -4 meter per second. So this will give you roughly about, let me see, 7.9 times 10 to the power 6 second. And if you convert that to days, so 864 or 846 just second to day. 1 day is something around that. So it will be roughly 91 days. Okay. So that means if you think of 1 micron particles or droplets, it stays for 91 days in the atmosphere. And if you do 5 size, if you say 5 micron, is you see the velocity actually depends on to the square. So 5 times 25 times is going to decrease. So roughly it will be less than, if it is 5 micron size, because diameter is to square. So 5 times square is 25. So this will be so 2 to 5. So 2 to 5 is twice. So that will be roughly 1/4 of that. So that many days it will stay if it is that small particles. But obviously it can evaporate. All that thing can happen. All right, so what you learned that it doesn't settle very quickly. It can stay for so long. So that's why it's important to know how far it can transmit. The last one is the removal rate. Removal rate is basically how many particles can remove per unit time. Okay, that's the removal. And so usually that if you think of number of particles per unit time would be the let's see what's the way to calculate is d by dt. So normally it's just you have to see what's the concentration in the particles. Rate of removal is roughly it's n velocity by h. That's the way you can think of this one is velocity is height over time. So if you think of velocity, that's dh over dt. So if you integrate this one, so that means the height it will cancel, so it will be number of particles per time. So if you write this equation, then you should be able to find the total removal rate. So you can plug the value and get the answers based on number of particles atmosphere has. So again, that's the based on the number of particles. So the n is not given here, so you don't have to calculate, but just know the equations.
I'm not sure if this is just my screen, but I can't see the very bottom of where you wrote. I see like the top of DH. Could you just scroll down a little bit so I can see what you wrote right there?
Do you see that? I don't see any other way. Let me see, because
That's okay. If not, I can just look at them after lecture then.
let me write it here. Let me write it again there. Removal is dn by dt. If you write the equation, that will be nh by velocity. Oh, I'm sorry, this is reverse. Velocity by height. The reason is if you say velocity is h over t, height cancel, that way it becomes the number. So you got to know the initial number, how much number of particulates are there. That's the way you should be able to calculate. Okay, so you learn how to do the modeling as far as the how long the drop rate will stay. As you learn here, they can move. Then you could be able to see those how far it can spread in the air. So first of all, what kind of particulates you should be, or what kind of pollutant you should be concerned about inside the home. The very first one that most of the time people do care is asbestos. The reason is a lot of those old buildings has pipes, asbestos as used as an insulator. So those insulations and rooftop, all those insulators are actually has asbestos. So most of the time people are concerned how much asbestos we are inhaling. So now no materials is used for asbestos, so it should not be there. But this is just one other thing. Carbon monoxide, we burn, we cook, all those things can inhale carbon monoxide. Also we exhale both mostly carbon dioxide, but there is also some very small quantity, but mostly it's because of the stove and gas. Then we have solvent. You use all the carpet, all those things. It has solvent or the kind of coatings for fire, to prevent fire or to prevent water. To you don't want to have a carpet that can wet easily. So that's why all these solvents are used. So you might expect formaldehyde is one of the solvent. Then you have small particulates because of smoking, vacuuming, stove, fireplace, all that stuff, you name it. If you're living in Los Angeles, the particulates can come from outside. In fact, where I live right now is in near the student housing. There is a big building, construction building. Every time I put, if you want to know how much particulates you might be inhaling, just take a sellotape, duct tape out and leave it there with the things and see how much deposited. You'll see tons of it. So I lived outside one time. It was like one day it's like very thick, and if I put my car outside, I see there's so much dust coming out in the parking area. That's because of constructions. So those are the particles we are inhaling without even realizing. And then also you have nitrogen dioxide, ozones, radon. Radon is something that's concerned in Culver City area because that's naturally produced from the soil. from radioactive decay. We'll discuss about that. Then sulfur dioxides, any kind of organic materials. If you heat, for instance, kerosene or coal, sulfur dioxide is emitted. If you are doing barbecue, you are inhaling lots of those sulfur dioxides, nitrogen dioxides, small soot or carbon soot. Those are things comes out during barbecue time. And volatile organic is also released during almost all these process. They are used for kind of solvent for your most of the coatings has those volatile organics. So those might be coming out. But most importantly, radon, that's naturally produced. So it's something you don't have any choice. If you have a house built on those area, you will be exposed to that. But there are ways to actually minimize that exposure. So for instance, in this picture, if you see, radon is coming from uraniums. Uranium half-life is 4.4 billion years. So naturally they are present in the soil. So they decay to radium. Radium decay to radon. Radon's half-life, so that's what is written here. How far it can stay, what it emits. So this is just radioactive decay. So the main point here is that they are naturally present and they can emit from soil. So the first thing you can do is actually having a layer of maybe find way that you can actually um, close it so that the radiation cannot go. There is um, no fractures, no kind of leaks, so that things can come from the ground. So you can maintain that leak, seal all the joints so that it doesn't have that. So that's the number one. Number two, so that's the source mitigations. And second, even no matter what, there will be always erosion, so that's why the source will be always present. So what you can do is have a clear, good ventilation system. So the here idea is that outside atmosphere, because you are living indoor, so that means things can build up, whereas outdoor things can, once it's emitted, it can be diluted very easily. So that means you are expecting that outdoor concentration of radon will be a lot less than indoor concentrations. So you want a ventilation system where air is circulated through the home system such a way that it can remove. And then you can have also a filter which takes the continuously pump the air inside the filters and then remove a lot of pollutants. So that's why the HVAC systems are important. So those are related to air conditioning, AC for air conditioning, V is ventilations. So these are circulation, H for heating. So all the system that you have in if your central heating facility, they use filters. So you must put those filters or replace those filters time to time to remove a lot of these pollutants. So now let's do this equations and now see where it is, how we can solve this one. So the first one is to understand the mass balance. So right near, as you see, mass balance is these are the components. The first one is you have incoming air, okay. So that incoming air, the infiltration concentration in air is Ca, and it moves at infiltration rate is I. So I think like a flow rate, okay. Then you have a source. Source is basically radons or anything that is, or you are cooking, all the things coming out. And then you have also a decay models. Decay means now some other particulates or contaminants can be removed because they spontaneously decay. Like I said, radon can decay in certain days. If you have particulate, they can settle. So those are the decay. And then you have indoor concentrations, C and V, volume of the indoors. And you have things going out of the system. Okay, so this is out. This is in. This is the source and sink. So your rate of change would be in minus out plus source minus sink. Okay, what remove out of the system will decrease the concentration, so change will be this much. So in fact, that's what is written here. Okay, if you see the equations, this is a rate of change of concentrations in indoors is whatever the source. This is whatever coming in, C air times number of, this is the concentration in air, is N is the number of, like I said, number of air change per hour. So this is more like a flow rate. Okay. And then V is the volume of the atmosphere. So this can be replaced as Q. Okay, Q is the flow rate. Okay, so number of time it changes the volume. So it's more like how far you can empty or the entire air. So that's more like residence time and how frequently you can change it. So then this is out, whatever leaving the systems from the bird, and this is decay. K is the decay constant. Usually air, this is constant air concentration in air. So if you solve this one for steady state means VdC over dt equal to 0. So if you solve this one, it will become C infinite, means if you stay long enough, wait long enough, T equal to infinity. So T equal, steady state means T equal to infinity. It means if you stay long enough that, or wait long enough, all the concentration become equilibrium. So if you solve for this one, you will get this answer. Okay. So what it means, steady state concentration depends on the source divided by volume plus concentration air and number of times you are replacing the air in the home divided by N and K. So what that means is this factor, number of times it replace, can also decrease the concentration, the dilute the source. But if your air concentration is high, then that means it also introduce more contaminant. So usually CA is negligible. Most of the time you are concerned about contaminant indoor. So outdoor concentration, most of the calculation people can ignore. But you cannot ignore if the source is actually outdoor. So for instance, here, the dust coming outside, um, the things. And so N, there is a chart window, somebody says, repeat what is N. N is number of times you are, so it's written here, number of air changes per hour. So if you have a ventilation system, how many, or just the circulation system, how many times you are emptying, replacing the air inside the door, indoor. That's related to flow rate. Okay. But if it's not steady state, this is the long equations. So what it means that you have the same constant here. Basically steady state, all these term become, this term become 1, this term become 0. Okay. But if you have non-steady state, you have this exponential term. So that's it has the C0. That means initial concentration indoor. Okay. So what it means that you have initially whatever the concentration you have, it will decay at certain rate, plus whatever the source and air will introduce this much of contaminants over time. So again, you don't have to solve for it. You just have to use this equation to solve any problems given to you. So this is more like a plug the value and get the answer. So we'll solve some questions related to that. So let's say some specific case. For instance, if you think of a pollutant which are not decay very quickly, for instance, carbon monoxide, how long it will stay. So that means you could, no decay means it's conservative, means it doesn't decay, K equal to 0. So that means stays forever. So in that case, you could put K value equal to 0 in this particular equation. So this becomes 0. So anywhere there is a K, that becomes 0. And then it becomes this value. So this is the concentrations for a conservative pollutant which do not decay over time. So the sink is 0. Okay, so what it means is sink equal to 0. And but if you assume that there is no initial concentration, means your house was clean to begin with, you can ignore this value, C0 equal to 0, then you left with this number. Okay. And a lot of times the case, your home is usually clean and then contaminants come from somewhere else. So that's how you'll have to calculate how long it before it to build up the concentrations. So for instance, you can use this equation to calculate how long the smoke will stay if somebody smoke inside your home. Okay. because the smoke will not decay probably, so that will be only emptied out by ventilations. So this is the way you can build up, calculate how long it will, how long you will inhale that smoke, if assuming the inhalation rate. Any question? Okay, so these are the source of pollutants. As I said, carbon monoxides, nitrogen dioxide, sulfur dioxide. There's a formaldehyde, which is basically a solvent. These emission rates are given. So if you have an oven, based on when it's designed, the oven emission rates are now decreasing with time. That's why you see the gas of, if you have gas, it has a lot less emissions than if you have conventional kerosenes or any other things. This is another thing. If you think of a cigarette smoking, the amount of carbon monoxide you create is a lot more. Lot more. So this is a 86 compared to 1900. If you are using the gas stove. Um, but but if you are looking for the nitrogen oxide, the amount is a lot less. Sulfur is again produced from coal or oils, so you will not produce much sulfur dioxides. So these are the different emission rate. That emission rate is sometimes you need as a source. Okay, this value. And same thing for decay rate. As you see, carbon monoxide doesn't really have zero. That means it stays forever. At least in indoor. In terms of hour, if you say per year, then it's a different value, but per hour, that value is zero. For sulfur dioxide particulates, as you see, particulates less than 0.5 is 0.48. The reason is it settle down quickly. And if you think of radon is very small, but still it's not zero. Okay, 7.6 times 10 to the minus 3. So these are the K rate, K value. You can use this table when you are solving any example questions. So let's solve these questions. This is basically how much emission that can happen if you have a heater that is used kerosenes. So it says an unvented, let's read this question, an unvented portable radiance heaters fuel with kerosene is tested under controlled laboratory conditions. After running the heater for 2 hours in a test chamber with 46 meter cube of volume. So this is volume is given, V, an infiltration rate, that's I. The concentrations of carbon monoxide reaches 20 ppm. So this is C. This is the C. Initial CO in the lab is 0. That means C0. This is C0 is 0. That means at time t equal to 0, C0 equal to 0, initial concentrations. And the ambient C0 levels is negligible through the run. So ambient means what is the concentrations outside in the air. So that means this is negligible. That means Ca equal to 0. That means the concentration in the air is 0. Treating carbon monoxide as a conservative pollutant, so that means K equal to 0. When they say it's conservative pollutant, that means K equal to 0. Either way, if you see carbon monoxide, this is already given 0. Okay. Then the question was, find the rate at which the heater emits carbon. So I asked what the source emission rate. If the heater were to be used in a small home to heat 120 meters cube of space having 0.4 air circulation rate, so that's how many times it circulates the air, ACH. Predict the steady state concentration. So I asked the concentration in home steady state, so C infinity. This is the volume of your home. This is the N. Okay. This is, I'm sorry, this is N. 0.2 air circulations rate. Okay, so everything is given. So at least first thing, any problems you are given, you have to first understand the different terms. Once you understand the terms, then you will be able to calculate. The first thing is to understand is the concentrations, concentration of volumetric concentration because it says 20 ppm. 20 ppm is not really volume term. It's a part per millions, right? So you got to understand how that is related to milligram of carbon monoxides per meter cube of air. So that's the first thing. Let's calculate C. So C is given 20 ppm. 20 ppm. This is carbon monoxide, right? So first you have to calculate in terms of milligram, how much that is in milligram of meter cube. Okay. So first thing you have to do is it's 20 meters. So that's 20. What's the molecular weight of carbon monoxides is because you have to change to milligrams. Carbon monoxide, carbon is 12, oxygen is 16, so that will be 28. Okay. So 28 grams. And then if you think of what is the um, concentrations, if you think of ppm, so that's pb equal to nRT. So in that context, there is a conversion factors of how you change to 1 atmosphere to 25 degrees Celsius. I'm going to write it here, the value here, 24.465. That's basically, if you think of what is given here, 20 ppm is 20, the volume of carbon monoxide or partial pressure is 20 when you have 10 millions of volume. So if you take, let's say, if you think of volume, what it means that if you take 1 millionth meter cube of volume, you have carbon monoxide occupies only 20 volume. So that's the V. So that's why you have to multiply this V is given. And then you have to change to, or the partial pressure is given. So that means you have to change to N over V, how that value is. So that will be partial pressure divided by, let's see, by RT. Okay. So partial pressure is given for carbon monoxides, and then that's 20 ppm, and then you change to use R and T, and then you'll get this number. Okay, for now I'll not write this one. We can put that in the campusware so that you know the detailed calculations, or you can check the book. Okay. But point is, you got the number. Concentration is 22.9 milligram per meter cube of carbon monoxide. Usually, I will not give you ppm. Usually, I give you the concentration in milligram per meter cube so that you don't spend a lot of time calculating that, because I understand how to. You guys understand how to convert unit before. So first thing is to calculate concentration in milligram per unit. So we already calculate that is 22.9 milligram per meter cube. Okay. The next thing, which is mostly what you learn here, solve the heater emission rate. Emission rate is S. Okay. So, and I ask what is the emission rate for the heater. So if you see, if you write these equations and rearrange it, so S would be CT, NV goes up, and then divided by 1 minus e to the power minus NT. Okay, there's a negative term here. So basically you are putting the value. This value is 22.9 milligram per meter cube. N is given, that's 0.25. Air, what it given is 0.25 circulation, air circulation per hour. Okay, that's what it means. SEH means air circulation per hour. And then you know also how much the volume of the N is given. The volume is what? Volume is 46 or something, 46 meter cube. So that's the here 46 meter cube. Okay, and then divided by 1 minus e to the power minus n equal to 0.25 per hour times time. Time is given, it says initial concentration. So it says somewhere it says, let's see. Emission rate. So what's the time? Time factor somewhere given. After running for 2 hours. Okay, so after running for 2 hours, this is time equal 2 hours. So that will be 2 hours. You should be able to get that value 669 milligram per hour. Again, these are things you are just writing those the value. Most of the air quality problems are not really difficult because you know the equation, you just plug the value. So say the next one is the steady state concentration. Steady state concentration is this, and you know that for this problem, C air equal to 0 and K equal to 0 because carbon monoxide rate is 0 and air ambient concentration is 0. So that means this value become ND. Okay. Again, source you calculated just now, 669 milligram per hour divided by this is a small home, that's what I'm asking to calculate. So your air circulation rate is 0.4 air circulation per hour, and the size of the volume of your home or air inside your home is 120. So if I put this value here, 100 n equal to 0.4 time air circulations per hour times 120 meter cube per air circulations. Okay, so this is a C per hour, and the volume of how much air is being transmitted is 120 meter cube per air circulations. That value you'll get based on what book, I'm just going to write it here, 13.9 milligram per meter cube. And again, if you convert this to, so this is given milligram per meter cube. If you convert to ppm based on partial pressure, you'll get 12.1 ppm. Okay. So that the emission standard, if you see for the home is around 0.9. I don't know where it is written somewhere. So 9. So this is the emission standard for carbon monoxide concentration in your air should be maximum 9 ppm. That's what if you see the carbon monoxide alarm, that's the one is set for 9 ppm. So anything above 9 ppm, it goes off. So that means it will go off if you have that at your home. All right, so there is another questions based on the radon concentrations. I'm not going to solve it. Again, this is example question in the book. You'll use the same concept to solve it. So try to solve these questions. Basically, it asks, let me read it so that you can solve by calculating.
On
So,
the previous problem for CA, why did you say it was 0? Because
CA is the ambient air concentration. It says that carbon monoxide, the air concentration in the outside air is 0.
okay.
And rate is 0 because carbon monoxide stays for a long time. Okay. This is ambient air. Means whatever the air you are circulating from outside is 0. Doesn't have much carbon monoxide, which you can assume most of the time, unless somebody is burning outside, some like during wildfire, you can assume that. Okay, so the next question was, suppose the soil under single-story house emits certain amount of radon gas. As a worst case, assume that all this gas finds its way through the floor into the house. That means all there is fracture, so it all leak. The house has 250 meters square of floor space, so that means this is the area of the house. Okay, so if you're talking about house, the area over here is 250 meters square. And average ceiling height, this is 2.6 meter, and the air change rate is 0.9. So that means this n equal to how far it is moving out of the system is 0.9 air circulations per hour. Okay, whatever the volume you have, it is removing almost near 1 times an hour. Estimate the steady state concentration of radon in the house. So again, I ask what is the steady state? Based on the previous equations, you can assume that the ambient air is 0, but you cannot assume k equal to 0 because radon has certain half-life. So S over V divided by N plus K. All I'm doing is putting Ca equal to 0 because outside you can assume this is almost 0. It's not accumulating. So S equal to this given, and we'll get to that point how we can calculate that. So let's write the volume. So S goes here, 1.0 PCI per meter square second divided by volume is 250 meter square. That's the area times the height, 2.6 meter, divided by N equal to 0.9 per hour plus the K. K is, it's not given here, but it's, I gave you in some problem here. So this is K, 1 over hour. So that's 7.6, 10 to the minus 3. 7.6 times 10 to the minus 3 per hour. Okay. The only issue here is that you got to, this is per meter square per second. That's the concentrations. You have to, this is all about in hours, so you have to change it to hours. So this is, so 36, 1 second is, 1 hour is how much second? So that's 60 minutes and 60 second, 1 minute, 60 second per 1 hour. So this is 1 hour. So convert second to hour. So that take care of the second term. Then the second thing you have to do is this is per meter square, the concentration. You have to, so this is the source means how much total emissions. So you have to multiply, this is per meter square of the space. So you have to multiply total amount of space you have it's emitting. The source is the total amount spent. So that's you multiply times the area, which is 250 meter square. That way the concentration become only in, the source become only in PCI. Okay. So once you do all that, you should be able to get, this is 1.5, 10.3 PCI meter cube. Okay. So this is the average concentrations of the radon gas if it's emitted at that levels in a house. All right, so we are almost end of this class where we'll discuss about very quickly about outdoor pollutions. Here, I'm not going to go details. The reason is I'm going to explain those in the examples problem. So I'll just go quickly so that you know the concept. So the idea here is that you have a stack like here, you see there is a certain height, and those once you those heights are emitting the whatever the emissions, and they go through that, it's spread, and certain things that is controls in control is h. That's the height of stack. The idea here is that if you emit too far away from the atmosphere, people who are living at the on the ground level, they are not exposed to that pollutant. That's why you see the stacks are much taller. The reason is they want to avoid that concentration pollutants. And second, usually the median or the center line is a little bit above the stack height is because the smokes are coming at a faster rate. So that velocity will lift them up a little bit higher. So that's why there is a little bit initial velocity that make them move a little bit higher. And once it's there, the wind speed is going to move them towards the right. And not just wind speed, there is always dispersion or diffusion because of the air circulations. Air is not 0 degrees Celsius or because air particle itself move around, so that Brownian motions and dispersion or the velocity itself will make them move sideways. And this is what's called Gaussian point source distribution. The reason is it means the smoke diffuse across the disperse across the central line in a normal distributions. It's not like, it's uniformly distributed both sides. So once you know this assumption, you can estimate the concentration of pollutant at the center line at any locations. Or you can measure the concentration at different locations far away from it. So number of variable you should consider is the distance, how far you are from away, and also the height, both height of the stack as well as the net height from the center line. That's based on the velocity of the how fast the smoke is rising, and then your wind speed. Okay, and all this dispersion in y directions. Y means spread across, and g means how above and below. The G one is important because that's the one it will spread towards the ground. So that's the one you have to pay attention to. The Y directions means across, how far it's dispersed. So for solving these problems, you need certain assumption. Rate of emission is constant. Wind speed is constant, which is not true. Wind speed is not actually constant all the time. In fact, wind speed can also vary from the locations. Near the ground level, the wind speed is low because of frictions. As you go up and up, your wind speed is much higher. That's why if you are living in a high-rise building, you will experience wind speed much more than somebody who's living in the ground floor. And there are a couple of assumptions. Pollutant is conservative. There is no decay. If it is decaying, then obviously there will be low concentrations. And also it doesn't account for the terrain. Means, if you're living in a big cities, the trees, canopy, they're all going to influence the distribution of velocity. So this is a very simplistic assumption. So we can solve that by using that process. Again, as I said, the whole Gaussian point distribution means it's a normal distribution, means it equally distribute to both sides. And the curve, the distribution curve is a Gaussian distributions. So my point is, how do you determine the concentration? This is what it is. We are not solving it. I'm just writing the final equations. You just have to understand what that means. So Q here is the emission rate. How much is coming out is Q. Okay. That depends on that. Can imagine if you are spreading the smoke, it will diffuse, it will go across. So what it can be diluted. So there are things that can dilute it. So that dilution factor is here. This is the dilution factor. Diluted by velocity, wind velocity. That's why the denominator, you can see um, the velocity of the wind speed. And also it can be diluted based on the how high it is from the ground, because you're looking for the concentration at the locations X and Y. So the taller the building or the stack, the less pollution you'll experience at the certain height, because it will mitigate. So that's why the H is at the denominators. And then you have a dispersion term, how much it disperses because of in Y directions as well as Z directions. We'll get to that point. That dispersion depends on the velocity as well as the molecules and all that. And then you have this exponential term that basically says how much it can spread across Y and G. So that again depends on this dispersion coefficients and the height. Okay, and all that written here. So now if you're given a problem, what the answer would be, you just plug the value and get the answer. So your goal 90% time will be identifying the different variables. So what you can determine is this and this you can estimate. Because as you see, these are depends on different factors. So you will be able to estimate those at different locations. And everything else will be given. So it's really not a difficult questions in terms of how to calculate that. And another thing is the velocity, wind velocity. It's average wind velocity at different height. Okay, so UH. So as you see, UH means the velocity at the stack height. But how do you determine the wind's velocity at the ground level or at different locations? So this is the equation you can use um, to basically, it's a power law. That means wind velocity can decrease as it by exponent of power P as you go down towards the ground levels. And that depends on what the wind stability is. So that's P value you can determine based on these tables. So as you see, based on stability class means whether it's a turbulent flow or the laminar flow, there are different way of calculating different stability class. So based on the class, which is basically related to wind velocity, if wind is moving very fast, it's turbulent. So that means the class will be C or D or all that stuff. Okay, I'm saying A or B. F is the very stable. So this p value changes based on that. So you're based on the wind velocity, you'll determine what kind of class it is, whether it's A or B or C. So you use table 7 to determine the class of stability. Once you determine this class, you go here and you apply that to calculate P. And once you know the P, you will be able to calculate. H is given, and G is basically you are determining the concentration at the height you want to know. For instance, if you are 6 feet tall, the G is 6 feet because that's where the nose will be. And because that's what you are determining, what's the velocity at that locations. So velocity you can calculate like this. And so this is the example given to you. Suppose it's basically ask you to calculate estimate the wind speed. So wind speed is basically u h by ua is h over g p. So this 10-meter ground. So this is g. Above ground, measure the wind speed. This is UA. And then I asked you what is the calculation, what's the wind speed at this number. So this is UH. So this is H equal to 300 meter. And it says rough terrain, and this give you the idea, rough terrain and the slightly unstable. So that means it will give you what's the p value. Slightly unstable is this. So the p value is 0.4. Okay, and it says p value is 0.4. So you plug the value and get the answers. Okay. So another time, as I said, you can determine the dispersion coefficient. These are the value given here. As you see, these value dispersion, how it can disperse, how far it can disperse. It depends on the velocity as well as the locations, how far it is away. So you can use this equation to calculate. So A, C, D, F are constants. And X is the distance. This is usually given to you, distance from the source. So A, C, D, F, how do you calculate that? You can calculate that using this table. So again, if you know the stability class, you can go back to this table, table 8 and 9, and you should be able to calculate those values. So it has two different factors. If X is less than 1 kilometers, you'll use this set of equations, CDF. If the X is more than 1 kilometers, you use these equations. So all these things are given. So any kind of homework questions on air quality is not really about solving mass balance, all that. You just have to know what's the equation to use and what are those constants based on the table. So in final, I expect you to print out these slides or just have it ready so that you know where to look for those numbers. So your assumption of those will influence your results. So that assumption is where you can lose point. It's usually given to you, always says that whether unstable, stable, or that. So I have this example here. I'm not going to solve it for a specific time because this is already written. What we are going to do is I'm going to upload more example problems, but let's learn what we learned so far. Because ultimately, we are learning all this class, this is almost end of this quarter. We learn different concept at the end of the day, what it means to you and how much you can use for different applications. So what I did is I put the problem here, the things to discuss among us and ask you questions about this. What does your mass do based on what you understand so far? So can any volunteer says, based on what you know, what mass really does?
The mass reduces the velocity of the of the particles coming out of your mouth, so so it greatly reduces the distance that they can cover.
Yeah, that's a good point. So first is it reduces the velocity. Okay, velocity goes down. So where this is related to, um, that's how far it can migrate. Okay, the advections. And I see in the chart window, Kathleen says that filters out some large particulates. That's correct. So the next thing is it filters out large particulates. Do you know what is the mask pore size is in the typical medical mask? If you think of N95, that's actually block viruses because that size is less than several nanometers. But if you're looking for the medical mask or the typical cloth, they can filter out anything less around 5, 1 to 5 microns. Okay, the pore size. So that means it can block most of the large droplets, not the viruses. So the Shruti says the reduced viral load. Exactly. So it can reduce viral load because it blocks um, lots of the things that come out. So what I didn't hear is that it doesn't say. It says that if somebody is also, imagine this is another case. Everything that we learn is if you are coughing, you are reducing the emissions to your surrounding. But if you are wearing mask and another person is coughing near you, it can block most of the droplets. So that means your inhalations or the amount of things you can inhale is going to drastically reduce. So that's why it is said that you should always wear mask to protect yourself as well as protect other people. One thing you have to understand that mask, it says assume that everything is moving through the mask. But as you see, if you wear the mask, like somewhere this area, there are empty area, things can get in. So that's why it says a lot of times people ask if you visit somewhere to doctors, they ask you to put a sticker here so that it can block all these things. Because the moment you inhale, it goes up like that. So now question is, how does the restriction help? Having the 6 feet rules and all that stuff. So we learned that how do you emit this one, but let's calculate this. How long the coronavirus um, droplet containing the virus can stay suspended in air. So again, here we are looking for the coronavirus size. So this, let's say 0.2 micrometers, 0.1 micron. So let's calculate that how long the coronavirus will stay as it is. Usually it's not the case. Individual virus do not stay. It's always with the droplet, but droplet can evaporate. That makes it smaller and smaller. Let's say how long the coronavirus itself will stay if it is 1 micron size. So can anybody calculate this value? So let's go back to the original number we calculated. I'm going to copy from there so that we can see that number right away. Okay, here it is. So what I'm asking here is change the number. Can anybody calculate this value? If you plug the value to, let's say 5 microns, because first is a droplet. So can anybody says what this value would be for 5 microns? So this will be 9.8 times this is the density. So that's 10 to the power 6 gram per meter cube. It's 5 times 10 to the minus 6 meter square divided by 18 times 0.0172. So what that number would be. So as you see, the only thing we are changing, instead of 2, it becomes 5. So let's do the ratio. This is the same question we had in the midterms. I asked the question related to virus and bacteria. So let's see. 2 to 5 is 5 divided by 2 is 2.5. So that means this square is this will increase by factor 2.5 5 times square. So 2.5 square would be 6.25. So whatever the days here, that will reduce by 6.25. So I'm just going to write that number here. So before it was 91 days. So for 1 micrometer droplet, it stays 91 days. Okay, that's one we calculate for 2 micrometer droplets. For 5 micrometer droplets, how many days it will stay? As you see, this is 91 days divided by 5 divided by 2 square. Okay, because that's the divided by the size square. That's how we reduce. So that will be 91 divided by 6.25. So which will be 14 days, roughly 14 days or 15 days. So that means if you have a 5 micron droplet, it stays that. But is it true that it stays that long? The reason is you have also evaporations, you have wind speed, a lot of these factors influence it. So that's, in fact, that's the reason. If you think of these restaurants, they create this kind of barrier. The idea here is that if you're standing here and coughing, this barrier will stick to the lot of droplets. Okay, and for them most of the time droplets goes down, it doesn't go up, because the wind speed has to lift it. So if a person is standing here, let's say me coughing, so all the cough will go up and then it will settle down. So that's why this barrier has to be higher than the people sitting there. So that's why you see they raise it up. So that means all the droplet will stay inside that one unless there is a wind turbulence that could move it up. So if you are living in a place where the let's see 5 point, let me see, there is a wait, isn't 5 by 2 square equal to 5.026? I don't know, maybe I have done something wrong. So 5 divided by 2, that's the third window. 2.5, no, 2.5 square is, yeah, 2.5 is 6.25. Okay, so this is correct. All right, so if you do the same thing for viruses 0.1 micrometer, what that size would be? So this will be 91 divided by, so this will be 1, this will be other way, it will increase. Okay, so what you have to do here is that this is 2 micron. So this is 0.1 micron divided by 2 square. So let's do this one. How much it will be? 0.1 divided by 2 is 0.05. So if I say 0.05 square, that would be 0.091 divided by 0.0025. So 91. Oh, that's 36400 days. So that means it can stay 100 years. If you see, if it's 0.1 point particulates, if the virus that small size, that's why, if it is really, really small fine particles, this will stay for many years. But that's not the case because there is always wind, there are rains, a lot of fall, a lot of things that can happen that could lower it down. But this actually gives you a practical example of how a decrease in small change in particle size can increase the concentration a lot more. So now that we learn all that, can anybody says what can you do to prevent the transmissions? Okay, the 6 feet rule, we didn't discuss that one. So if you think of a person is coughing here, I'm just going to make my diagram. So this is coughing. My point is this will move like this. So why 6 feet distance is effective? Okay. So when you are coughing, you have an initial velocity. Okay, that's and you have also a settling velocity. Okay. So now you got to know that how far it before it disperse away. So for this one, you got to calculate using this stack velocity calculations. Okay. So think of this as a coughing. People are coughing at that point. So these Q emissions will determine by that. And then imagine this wind speed is basically your coughing velocity. So if you put that there, you'll be able to calculate what the concentration would be as you move further and further. As the x is, this is x here equal to 6 feet. You should be able to calculate that. So a lot of times if you do this exercise, you'll find that it remove most of them, but not necessarily all of them. So the risk is not really, if somebody is actually coughing and you don't have a mask, you are actually inhaling many of those particulates. So that 6 feet rule is actually not true if you are doing indoor. But if you are doing outdoor, that can be dispersed. That could be a lot of other factors. So it decreases, but it's not zero. That's why that 6 feet rule without mask is not effective. So they still make it because they assume that people are not coughing, they're having mask, all that factor. So don't trust that 6 feet rule unless people are wearing mask. So that's the take home message. All right, so that's all for what we discussed in terms of the class. But now it's time for you guys to ask any questions related to air transmission that affect you in a way. Any questions on that aspect or in coronavirus or anything else?
Yeah, I have a quick question on the last thing we were covering. Those ratios that you were expressing, like the 5/2 squared,
Yeah.
what how are you forming them? I just think I'm getting confused a little
Okay,
bit.
so that's exactly the size. So velocity of, let's say velocity of a particle. Okay, that's basically you have a bunch of constant time d particle square, right? You have all these things over here, 18 density and viscosity. Okay, so these are all constant. So basically what I'm saying is velocity of a one particle is the size of the particle square times a constant. Velocity of second particle will be that same constant because it doesn't change, the condition doesn't change. Only thing you are changing is the diameter. So if you do the ratio, that velocity by velocity 1 by velocity 2 is the diameter of particle 1 by diameter of particle 2. So when I calculate the other one, I divide the ratio of the diameters.
Got it. That makes sense. Thank you.
All right, so that's a good question. But any other questions? So here is my questions. What are the other rules that we didn't cover in coronavirus time? Can anybody says what you remember? One is 6 feet rule, another is mask. What about other? What's the another rule that we don't discuss here? What they ask you to do when you go outside and come back home?
Wash your hands.
Wash your hands. So what it does?
Sanitizes.
Basically, if you wash a hand, what you do is you increase that K, the decay rate, okay? Because this particular type of viruses, they are very sensitive to surfactant. So if you wash your hand, the soap, what it does, you see that very early video, we have this big viruses with this coating, protein coating. So it open up that entire the surface. So this virus will burst if you have in soap water. And what about inside the door? If you're living inside the door and you have indoor and you have the ventilation system, and also people thought about the other way, like if you're using the same ventilation system, let's say our is central facility. That means all the air that come into our home is basically the um, the air we are inhaling from other people. So how that helps now? How do you minimize that?
In
So
the
that's
filter for your
yeah.
AC, they have some antimicrobial ones or some that have really that can filter out some small particulates.
So that's why you got to ask them what do they remove their filters and change their filter recently or not. Number one. Number two, they have to increase the circulations. Whatever the normal circulation rate you had, you have to increase it much faster, because you see what you learn in this class, that n value is the important value, number of times you are circulating the air. So that has to change, and also the filters. So wash your hand, because you're decreasing the K, increasing the K rate. Number two, increase the circulation rate in value. So that means you are diluting it as faster as possible. Open your windows so that things will go out. So that's one of the reasons why the coronavirus transmission rate increases during Thanksgiving is because people migrate, travel to different place. Mostly in the cold place, they are air conditions. They are living inside the door. In Los Angeles, you can open the windows without having to worry about it. So you might expect the transmission rate will increase drastically in places where it's cold climate. First, you get sick much faster, and second, you are staying indoor. So the emission rate will increase a lot. That source term will be increasing because you are staying inside a lot. So that's all the reason why things has improved or not improved, got worse. All right, so that's all of the things that we wanted to discuss today. Next week, again, we'll discuss about finance. We'll discuss about also the sustainability aspect of this class. So you'll apply all this concept. So this will not be quantitative. This is more about discussion, all that stuff. So I hope you attend those classes, because I see that the number of um, attendance has been decreasing. Anyway, I will release the midterm score in the Thursday night, so that you can decide your whether you want to take pass or no pass. But right now, I think it's I would say just prepare for the final, because that carries a lot of weight. And we have another quiz next class. That's again, this is your chance to improve your old quiz. Best of two will be carried over. So that means this is an opportunity if you didn't do well before. So I look forward to seeing you the last week of class. After that, I'm sure you all will looking forward to this break. So let's meet you tomorrow next week and attend the office hour. This next week will cover most of the final questions. So last year final questions, I'll also share like 10 or 15 extra questions to solve so that you get a lot of practice. So attend all the office hours as well as the TA hours. All right, so that's all. See you next week. I'll stop recording now.